Okay, so good morning, and I think we have finished with differential pair frequency response. Am I correct? We have finished with that or still remaining? So how to find the pole or a zero intuitively at the mirror node, at the output node, input node, the node which is source coupled. And is this complete or there is something remaining? We have done till this slide. Okay. So that means now we are going to move on to the next thing. So if I simply show you this circuitry, look at this. Can you identify, though I have shown, how many poles and zeros will this structure have? I request Goa campus students also to look at that. How many poles and zeros will this amplifier will have? So it is shown also, you will have a pole at this is a mirror node. Remember, this is a PMOS differential pair, followed by an NMOS common source amplifier. Okay, so it will be a mirror node. So mirror pole will be there, mirror zero will be there. This is the output. I will have a pole at this node. At this node, we have the input going to the CSA. At CSA, you have a CGD. So CGD will have a component here, gain times gain of that of common source amplifier. So A is actually A2, second stage gain. And this will also give me a component at the output, and that output I will add to all the parasitics. I will add to the next stage load. That will constitute a complete C load. So I will have how many poles? 1, 2, 3. I will have how many zeros? 1. A 0 at this node because of CGD. Okay, two configurations are there, cascade of 2 stages. So 1 0 coming from the mirror node and other 0 coming from the CGD of the second stage. And then whatever input you are getting or not, according to input pole, input 0, that is, will add or will not add. Depends whether you have a R signal 0, R signal some value. Okay? Clear? Goa campus? Huh?
Yes, ma'am.
So if I show you another structure, identify how many poles and zeros will this have intuitively. It's a fully differential amplifier. So this will give you a maybe input pole and a 0. Output pole will come. Okay, 2 output nodes. A pole will come and then a pole at this, and remember this is a common source amplifier with P input. So you will have a CGD over here. So that will introduce a 0, a feed forward path. Okay, main signal path is from V out to this intermediate node to V. It's a signal path. So anything that is coming within the signal path directly or indirectly is going to introduce a 0 and a 4. Okay. So look at the structure of 2 cascades or this cascade. It is actually a fully differential pair followed by common source amplifier. It is a fully differential topology because I am using two common source amplifiers. One at each output of differential pair. But then it is a 2-stage configuration. So total gain will be gain of differential pair multiplied by gain of common source. Common source. Clear? Look here. So given us here, you have to speak in the mic.
Why we are not considering a pole at the source of M1 and M2, which is connecting it to the current mirror?
Source of M1 and M2. You can consider, as I told you. Normally these go to high frequencies, but as I said, you find the time constant at this node. Find the time constant. You have to find the time constant. Okay? So this will introduce a pole or a zero accordingly. In common mode operation, this will give you a zero also. Because it would be similar to a common source amplifier with source degeneration. So you will get a zero also. Remember that. Any other question? So when I say intuitive analysis, means some idea about the circuitry. So I need not go to a very great detail of finding out the accurate values, accurate expressions. But can I have a first look at a circuitry and I can have some idea about the frequency response the circuit is going to have. And a little bit of idea about which node is going to introduce a dominant pole. Clear? So this saves a lot of time because mentally, through my own experience gained over the period of time, I can apply those formulas, I can use my previous results and come to the, or get the expressions without much effort and without much time. So this is an ability that every analog designer should develop. And this aids in synthesis also, because this gives you a great understanding, a very good understanding about the circuit behavior. That if I make a change at this particular node, how does the other nodes vary? How does the frequency response change? How does the swing change? How does the ranges change? All these things. So now normally we use amplifier in a feedback mode. Normally. Reason is, why do we use mostly op-amp in a feedback mode? What is the reason? Bandwidth increases, okay, one reason. Stability, okay. No, I'm saying I'm not going for stability, maybe distantly related. What is the one main reason why people go for op-amp in a feedback mode?
Feedback mode, we can configure it for our own gain. Exactly.
That I can do in common source also. Can't I configure the gain there? If I need higher gain, I can go for cascade. If I go for still higher gain, go for 2-3 stages together. Maybe 3 common source amplifier together. So what is it that benefits me when I configure a op-amp in a feedback mode? Goa campus, anybody having any idea? Right from the very first class, I am shown a unity gain follower, a non-inverting amplifier, inverting amplifier, where there is a connection from output to input. Precision circuits, rectifiers. I can make rectifiers by using diodes. I can make rectifiers by using BJTs. But then why people prefer op-amp? You have a rectifier using an op-amp also. Why? Oscillators. You can have a tank circuit and generate. But then I prefer a op-amp to behave like a, or circuitry to configure a oscillator. Reason. What reason? One main reason that helps me in configuring or by configuring op-amp in a short feedback mode. It is called as something called as the reliability of the circuit or the fluctuations in the circuit performance. That gets limited. Fluctuations get limited. What do you mean by fluctuations? Suppose I am designing an amplifier. I want a gain of 10. And if gain is depending on temperature fluctuations, voltage fluctuations, VT fluctuates, okay, the gain shifts by plus minus 10%. So either sometimes I will be getting plus 9 or sometimes I will be getting minus 9 or 11. Why not 10? Why not 10? Why 9 and 11? Why is there a window? I do not want this window. Can I say to my user, you will get a gain of 10, plus minus 0.1%. Window, I need window to be very, very small if at all it exists. So I want reliability. This is reliability. And this is what we achieve through negative feedback. This is what we achieve through negative feedback. Okay, why? Because very simple understanding of this negative feedback. If gain is increasing, then your net input gets decreased because it's a negative feedback. Because net input is nothing but the actual input minus the fraction from the output. It's a negative feedback. So if output is increasing, more is getting subtracted. Input comes down, so output comes down. If output is decreasing, less amount would be subtracted from the input. And actual input will go down. Will increase. So output will also increase. So even if there is a fluctuation, still I will get a gain of 10. That is why we configure inverting amplifiers or non-inverting amplifiers, where we say that the gain is given as minus RF by RI. Where RF and RI I configure 10K by 1K gives me 10, a gain of 10. Then somebody will say, why are you using A then? Why using a very high gain amplifier? You are wasting resources. You are using a gain of 1000 to get a gain of 10. You are using an op-amp whose gain is 1000, 10,000 to get a gain of 10. I will say, no, I am not wasting because I am getting reliability. Now I can claim that my gain will always be 10, no matter whatever be the fluctuations. I have gained the user faith in me. That design that he is going to give me is going to be a reliable 10. It's not going to give me fluctuations, sometimes 10, sometimes 9, sometimes 11, no. So I'm not going to give him a range. I'm saying you will get a gain of 10. This is what we achieve through negative feedback. That is why mostly because of reliability purpose, okay, because process variations they reduce to virtually nil. Effect of fluctuations they reduce to virtually nil. This is what we obtain through negative feedback. So that is why we say stability. Now circuit is stable. According to me, circuit is stable at gain 10. Circuit is stable at gain 10. This is one meaning of stability here. Negative impedance improves, negative feedback improves stability. But stability has another meaning also, which we'll discuss in terms of frequency response. But I can extend its definition. So it gives me more reliability of the gain. Effect of fluctuations on the circuitry reduces to nil. Always remember this concept. That is why negative feedback is a very important concept in design. I think you all must have read it in your control systems. Any system, mechanical or civil or electrical, though here we focus only on electrical system, you can stabilize them by using negative feedback. Fine. So now we move on to, I think we have covered what we have covered till this class. It was a very, you can say, it was a discussion starting from the simple common source amplifier. Okay, then we said, okay, common source amplifier is a single stage, what other configurations are possible? We looked at them. We looked at their DC parameters, low frequency, small signal gain, R in, R out. Then we say, what is the impact of high frequencies, signals? How does these circuits behave when there is a high frequency signal given? Accordingly, we say that parasitic capacitances come into picture. So every node now becomes a capacitive node, and hence there is a time constant associated with it. So finding of poles and zeros. So we did this for a single stage. We did the same analysis for 2 stages. Or now you can extend the same concepts for 3 stage. And in the 2 stage we saw maybe a common source cascade, or a common source cascade like we have in differential pair, where they are source coupled. It's not exactly a cascade, it is like a source coupling. Okay, then we went on, or a cascade which is a CSA and a CGA kind of a cascade. Okay, so we looked at all possible angles of a circuitry, various combinations which are possible, various ways of analyzing various modes of operation. So common source never operates in common mode. It has only single node. Whereas difference amplifier, it operates in the difference mode as well as the common mode. Accordingly, if you go for common mode analysis, how do you analyze a circuitry given a half circuit concept, not using a half circuit concept, but rather folding the circuitry and then doing the analysis, finding out R out, what are the ways of increasing impedances, what are the ways of increasing GM, if there's a source degeneration, what happens to GM? So we looked at all these concepts. All these concepts now they are forming your base, knowledge base for analog design. These are all small concepts that you have learned. Little bit in your first degree, refreshed and revised in this article. Okay, so once this base is thorough and you have enough practice, that will aid you a lot in designing circuit. So we can now build up on this knowledge base to move on to the next level of analog LCD. Okay, have we discussed current mirrors? Current mirrors we have not discussed at all. Reference also we have not discussed at all. So let me first tell you about now op-amp. We are starting with op-amp. So I will not touch the current mirrors right now immediately. But then how do you use, what are the various ways in which an op-amp can be configured? So op-amp is not a device. Okay, op-amp is actually a circuitry, which is normally two-stage. Or if not two-stage, a cascaded one-stage. And even if it is not cascaded one-stage, a simple differential pair one-stage. Okay, so in how many ways you can configure an op-amp? So looking at a circuitry of an op-amp, if I say this is an op-amp, give me intuitive poles and zeros intuitively, locations. Tell me which node will introduce a pole. Tell me what will be its DC gain, the swing, the OCMR, the ICMR. So just by looking at the circuitry, analysis you can always do. Small signal analysis is something that everybody should know how to do. Every engineer should know, electrical engineer should know how to do, electronics engineer should know how to do. Doing this any. Okay? So if I move on to op-amp, let me have the slide, it's not here. So what are the different op-amp structures you can have? Look here. One by one I'll keep on flashing the circuits to you. Okay. One stage, first of all, one stage op-amp. Both single-ended and differential topologies. One stage. Simple differential amplifier. A very simple differential pair which is a fully differential topology and single-ended output topology. So one is, this is single-ended output, this is fully differential. You know how to analyze these circuits. Analyze in common mode, analysis in difference mode, analysis with current mirror as a load. The behavior of node, source coupled node, the behavior of the output node, the behavior of the mirror node. Swing, how to calculate swing, how to calculate ICMR, how to calculate OCMR. And then the locations of poles and zeros. Anybody having any problem in this before I move forward? Yes, Goa campus? Anybody facing any trouble in this?
No, ma'am.
So we move on to the next, that is for a high gain. Now I want to increase again. Look here. If I want to increase again, look here. What am I doing? Cascoding. Cascoding in the input. This is a driver section to which I am feeding the input. This is the load. So I am doing cascoding in both. In load section, that is the upper section, and the driver section, which is the lower section. And here you have the ISS. This is my source coupled node. This is a single-ended output. So what type of mirror you are using? Cascode current mirror. It's a cascode current mirror. If you have a fully differential topology, you will not have a mirror arrangement. It would be simple two-stage stack over here. Here also simple two-stage stack over here. Find out all those parameters that we have been calculating till date. And the locations of poles and zeros. Now move further. This is again a telescopic op-amp or use of cascoding in single stage op-amp. We call this as a telescopic op-amp. Both are single-ended, but what's the difference? In one it is a cascode current mirror. In another I have changed the connection. This connection has been changed to this. This is known as a low voltage cascode connection. Low voltage cascode both operates in saturation region. But then this is fixed at, this connection is made to save the net, headroom voltage, the net voltage required by this. This is known as a low voltage cascode. But both are single-ended, both act like a mirror. But then to save on the net voltage, which is required by the two transistors in the PMOS to operate in a saturation state. This is done for that. Have we discussed this low voltage cascode? Not yet. Okay. So move on to next. That is a triple stack or a double cascode. We do not use this. It is never used because how many transistors you have in one single arm? 7. And to bias, suppose each transistor requires 0.2 volts. How many voltage you require to bring all of them in saturation? 1.4. Minimum 1.4. So that means your VDD has to be more than 1.4. And if you have a VDD of 2, at the most your swing can be only 0.6 volts. And bringing all 7 transistors in saturation, very difficult. You cannot set because you may be able to set at one particular point, but moment there is a fluctuation, temperature fluctuation, your whole system will go haywire. It's very, very difficult to bring transistors in saturation. So we never use this, though theoretically this configuration is possible. But we never use it. Even single cascode is sometimes very difficult to bias. It is not easy, particularly in the feedback mode. It's not easy to bias a single cascode or telescopic op-amp. It is not very easy. Move on to the next. Yes. What I am doing over here? What is done? A simple differential pair is shown, and you look at the next configuration. What is that? This is converted to this. What is this? What is this? What I am doing, each arm is folded. Remember folded cascode? It is a simple cascode. I am not showing the upper section, I am showing a symbolized upper section. Otherwise, you would have had a transistors over here. I'm just putting a symbol, and then you have a cascode. So I'm going for a folded cascode. So this is my folding point. So I'm folding. So what I am doing is that this is remaining constant. This M1 is folded up. So look here, this is remaining same, and this is remaining same, and this is folded up. Arms are folded. Each arm is folded. So can I show you? Let me see if I can. I think I showed you how to fold. I showed you. Do you remember how to fold? Goa campus? Do you remember how to fold the structure?
Yes, ma'am.
So if we look here very carefully. So you are folding this transistor up. So it is this transistor which is becoming a PMOS. And then a folding arm. Yes?
Slides are not visible.
Slides are not visible. Is it there?
No, ma'am. Yeah, ma'am.
Huh?
Yeah, it's coming.
You have got, okay. So it is actually, each arm is folded. So this arm is folded. So this M1 folds here. So that means, look at this arm, it is folded up. Similarly, another arm is also, this is also folded up. So you have this arm folded up. Because these two are connected at the source. So here you have a connection at the source. Two PMOSes. And then this is going to, here it goes to ground through ISS. So this node will go to VDD through ISS. Okay? And then each one is a folded arm. So you have a fold over here. And because you have to have a current ISS, means current I1 and a current ISS by 2 through each arm. So I need to complete my circuitry, so I have to put a current source here. It's a folded architecture, a folded differential pair, or a folded cascode differential amplifier, or simply folded cascode op-amp. Because if I say this is my op-amp, so this will be folded cascode op-amp. Clear? A folded cascode op-amp. Now I replace these symbols by a current mirror. Replace them by a current mirror. So put a transistor over here, put a transistor over here, and a transistor over here, and a transistor here, and a transistor here. This is your output point. Now look very carefully. At this point, below this point, 1, 2, a stack of 2 transistors. Here also 1 and 2, a stack of 2 transistors. Up this node, if you put only one current mirror, it would be 1 transistor. So net R out at this node will be, what is the structure, what is the R out below, what is the R out of this combination? Assuming you have a transistor over here. Yes? Yes? Do we have Mansa there at Goa? Can I ask Mansa to reply? Yes, what is the R out of this structure? M3 and this transistor over here.
1 by GM parallel.
No, it will not be 1 by GM. This is NMOS. You are looking at the drain. it is an
R0.
NMOS. Yes.
R0.
Yes,
Is it-
please. You have to simply apply the concept of source degeneration.
Source regeneration. So it will be no, not 2 GM. That is 1 by GM3 into R03 into R01 plus R03 plus R01.
GM3, RO3,
RO3 into the
RSS1.
RSS1 plus RSS1 plus RO3.
Very good. So this would be, and then if you put it parallel with RO up 1, what will be the net R out at this node?
R01.
RO. So I do not want RO because otherwise the high R out of this structure will have no meaning to me. It will go wasted. So I need to go and cascode over here. I need to do cascoding. So it should be a stack of 2 transistors here. So replace I1 by a stack of 2 transistors. Replace I2 by a stack of 2 transistors. Now keep this in mind. Replace ISS1 by 1 transistor. And replace ISS by maybe 1 transistor. So how does the structure look like? Look here. How does the structure look like? So this is V out, a stack of 2 transistors here. This is M3 already there. Now this is 1 transistor. A 1 here, complementary, and then 2 transistors. This is your differential output. This you may replace by a simple current mirror or a cascode current mirror, whatever be the requirement. Okay? This is a folded cascode op-amp. Now I call this as a folded cascode op-amp. So, by folding the cascoded differential pair, we obtain the folded cascode op-amp structure. Can you tell me the number of poles and zeros here? How many poles? If I say first of all the dominant location for dominant poles only. Otherwise I know what you will say, every node will give you a pole. So there would be so many poles. Okay. That would be fine. So you will have a pole, this will give you a pole here, a pole here, a pole here. It's okay. So tell me which nodes will give you dominating poles. That means their values will be small. Which nodes have the potential to introduce dominating poles? Which 2 nodes? Let me ask only 2 nodes. Which will have the highest time constant? Suppose you have a C load present at the output. So which 2 nodes will have the highest potential for becoming the dominant pole? Yes? Who else is there at Goa? I don't remember the names. One is Manasa, who's the other girl?
Ma'am, I'm Kirti.
Kirti. Yes, Kirti. Tell me the one node which has the highest potential of introducing dominant pole. Yes? Somebody else? Can you give me a hint? Yes? Okay, Kirti. Which has the highest R? Which node has the highest R out?
Highest R out.
Yes.
I think
Which
it is.
node? Yes.
I think it is the output node.
Correct. Because the highest R out is going to be GM RO square parallel GM RO RO parallel RO. Am I correct? Because GM RO coming from the upper section and GM RO into RO parallel RO. So this node has the highest R out, and if CL suppose gets also large, so this will introduce a dominant pole. Output will introduce a dominant pole. Apart from this, which other node can give you a dominant pole? Which node has the potential to introduce a dominant pole? Do we have any other node? What is the R out at this node? What is the R out at this node? It would be RO down, it would be RO parallel RO. Something here and then something coming from upper section. What it would be? What value will you get from the upper section for resistance? You are looking at node X. Yes, who can do that? Goa campus. No. It will not be 1 by GM. You have to use the common gate amplifier result here. Yes, Goa campus. You are look at the structure M3, M7, M9 as if you are looking at the source of into the source of M3, because X is the source of M3. So if you use the common gate where input is at the source, so what is the R in relation? That you can use here. Yes, what is RD here? What is RD here? RO, it would relation for R in of a common gate I can use here. So net resistance load is RD plus RO divided by 1 plus GMRO. So what is RD here? It's a cascade of 2 GMRO square. So replace RD by GMRO square and then do the calculation. Neglect 1. What do you get? Roughly how much value will you get if I take all GMs same, all RO same? Approximately. Yes? Yes, Goa campus.
RO square.
RO square divided by, there's a denominator also, bache. GMRO square divided by, neglect 1, you will get a GMRO. Clear? Yes or no? Have you able to do the calculations? Okay, who's the first boy? I think he is Nisarg. Who's the second one?
Sriram.
You are?
Sriram.
Shriram. Okay, Shriram. So, what is the net R out you are getting?
GMRO squared by GMRO. So it's RO.
Good. RO. So, you have RO from the upper section. From the lower section, it is RO parallel RO. So, what is the net R out? RO parallel RO by 2. So, and you will have parasitics at X coming from all the transistors M3, M5 and M1. Their components will appear as a capacitive loading at X. So, you will have a pole. That will give you a pole. So Cx you estimate. What will be Cx? CGD coming from M5. C drain bulk coming from M5. C gate source coming from M3. C source bulk coming from M3 and C drain bulk coming from M1 and C drain to gate or CGD coming from M1 plus interconnection parasitics. That will constitute Cx. So you have a CGS component because we know CGS is dominating. So that will give you a pole. So resistance is only RO. This resistance is GM-RO square parallel GM-RO square. So this may not introduce a dominant pole. This may not introduce a dominant pole. Got it? Clear? So what about, so you have one node and the second node. What may be this? What is this? If I ask you to find the node, time constant of this node. It's a PMOS. At this node, PMOS up. Looking at the drain of PMOS. So RO, looking at the source of PMOS down. Again RO, just now you have calculated. RO parallel, RO. Rather it would be RO parallel, RO. Because at this node you have. So you have to make appropriate adjustments because at this node is actually RO parallel, RO coming up. Okay? So find out the pole. So this pole and this pole will be non-dominant. Whereas this will give you a dominant pole. And you may have a pole at the input also. You may have. So can you see a folded cascade architecture has only one dominant pole? Though it is something like a two-stage architecture. But you are getting only one dominant pole. As I said, lesser the number of poles, better, I will say, good is the frequency response. And this is much easier to bias also. It is very easy to bias this. So folded cascade is a choice. Is the choicest architecture. People, they prefer folded cascade. Am I clear? Shri Ram? Yes, no,
Yes,
Manuka, Shri Ram, Kirti, I can now remember few names, Nisarg.
Yes, ma'am.
Yes, ma'am.
There are other few people sitting at the second bench. May I know your names?
Ma'am, Akash.
Akash. Second one is?
Srinivasulu, ma'am. Srinivas.
Srinivas. Okay. I will try to remember you people so that I can interact with you. Srinivas and first one is Akash. Okay. Sorry. Fine. So we have got a folded cascade of amp. And you can intuitively at least have an idea what type of response you are going to obtain. Clear? Now we move on to the next. Yes. If it is a folded cascade, can you give me the ranges? OCMR and ICMR. Yes. So let me go back. First of all, look at this architecture. Assume an overdrive of 0.3, VT of 0.7. Compute OCMR and ICMR. Because you may be asked, you should know what is going to be the range. Where should you have your DC level? In which range? Your signal can be there, common signal. Find out ICMR. I'll be asking Akash to tell me. Yes. ICMR and OCMR. Look at this slide. I'm opening it up for you so that you can cross-check. Folded cascade. Now remember, there is a difference. This is a folded cascade with P input. Okay? This is a folded cascade with N input. Clear? Hardly matters, doesn't matter. Only thing is that this is the folding node in this, where with n input the folding node becomes this. Otherwise everything remains the same. You have changed your input pair from NMOS to PMOS to NMOS. So what is the ICMR? Though it is not shown over here. Input common mode range. Look at this node. What is the minimum limit? VGS plus 1 overdrive. What is the upper limit? Upper limit comes from the drain voltage. Whatever is the drain voltage plus 1 VT to it. Remember? Remember? You have to find the drain voltage and add 1 VT. You will get the upper limit for the ICMR range. So what is the drain voltage? Highest possible drain voltage. Look at this node. Highest possible can be VDD minus 0.3. VT is, V overdrive is 0.3. So highest can be 2.7. So 2.7 plus 1 VT gives you 3.7. So my upper range will get fixed to VDD. Because 3.7 is more than VDD. Clear, Akash and Srinivas?
Yes, ma'am.
Okay. Now there is something else also. Lower limit at this node, you have another path that can fix. One path at this node comes from this path. There's another path also. Look this. There is another path existing till ground. You have to look at that path also. This path should also operate. So for V in minimum range, if you look at this path, what is the minimum possible? Minimum is minimum drain, which is possible here. Minimum drain. What is the minimum drain here? Look here. This is one overdrive. Another overdrive. And a third overdrive. So for all these three to operate in saturation, minimum I require is 0.9. So 0.9 plus 1 VT is 1.9. This is the minimum you want. Okay? So this is 1.9. How much is this giving you? This is how much? 1. And this is 0.3. So if you have 1.3 over here, will this path operate? Justify? Yes or no? If you have 1.3, this will operate, I know. If you have 1.3, will this path operate? If it is 1.3, okay, so drain voltage will be minus 1 VT. It is 0.3. At 0.3, this will not operate. This will not operate because minimum you require is 0.3, 0.3, 0.3. Clear? So minimum you want at this node is 0.9. 0.9. So if I have a 1.3 here, can I not have a 0.9 here? You can have. Because minimum is 1.3. So minimum at this point is 0.3. It's a minimum. You can have more than that. Nobody prevents you from having the voltage more than that. If minimum is 0.3 here, that is minimum at this point is, minimum is 1.3 here. So minimum you want is 0.3 as far as this path is concerned. But it can be more than 0.3. It can be more than 0.3. So if this node comes to 0.9, my circuit will also operate and this path will also operate. It hardly matters. So 1.3 does not say that you cannot operate this system. Your drain voltage cannot be 0.9. It can be more than that. Only thing is that minima is 0.3, that's all. It can be more than that. Clear? It can be more than 0.3. But highest should not be more than 2.7. So in between is your 0.6, 0.9. That you can always have. Okay? Look at the drain. Range is 0.3 to 2.7. If 0.6 comes in between. So what is ICMR? It is 1.3 to 3 volts. 3. Clear? What is OCMR? Now very carefully. It's shown in the slide also. OCMR means this output. So to the ground, how many paths? One path. So 0.3, 0.3, 0.6. Lower limit. You also have a lower path to ground. Look here, this way down. This is also with respect to ground. So move from this path onwards. Plus 0.3 minus 0.3. Sorry, this is plus 0.3 minus to plus. Plus 0.3 minus 0.3. Sorry. Plus and this minus. So 0.3, 0.36 minus 0.3. Only 0.3, which is this limit. Okay? And what is the minimum? So suppose I have a feedback also. Unity gain for follower mode. Output is connected to input. Then you will have one more path. This node is connected to input. You will have one more path to ground from here to here. That would be 1.3. So choose the one for which all the three path operates. So that would be 1.3. Okay? Similarly, find the upper limit. So do this exercise, and next time we will do more in this.